Okay, we have learned the concentration loss, the overpotential, and the limiting current density, and how to calculate the limiting current density. Then now let's solve one of the examples for the concentration loss and the limiting current density. Let's consider a fuel cell operating at 80 degrees Celsius. In the cathode, humidified air at 1 atm is supplied with a water vapor mole fraction of 0.2. And calculate the limiting current density JL for this cathode, assuming that the diffusivity of the oxygen in humid air at the temperature is 0.1 square centimeter per sec. But actually they use 0.2. And that the cathode is 500 micrometer thick and 40% porous. The porosity is 40%. And okay, this is the first question, and the second question is calculate the concentration over potential experienced by this fuel cell if it is operating at a current density of 2.0 ampere per square centimeter. Assume that alpha equals to 0.5 and C equals to 0.1 volt. Okay, there are two questions. To solve this problem, firstly, we should calculate the current density to calculate the concentration over potential. Because, as we learned, the concentration over potential is expressed in terms of the constant C, ln JL over JL minus J, operating current density, and this is the limiting current density. And in here, C has the unit of volt, because this term has no unit. This is because this term is unitless. That's why we should get the unit in C as a volt. So this C is 0.1, and what is alpha in here? Alpha is the transfer coefficient, which determines the kinetic rate of this reaction. Okay, then let's move on to solving the limiting current density first. How can we determine the limiting current density and how to calculate it? The limiting current density is expressed NFD effective CR0 over delta. Okay. So in here, N is the electron number, and F is the Faraday constant, and D effective is effective diffusivity, and we should calculate it to obtain the limiting current density. And what is CR0? This is the concentration of the air, the reactant, which is oxygen, right? So concentration of oxygen at flow channel, right? And what is delta? Delta is the thickness of the GDL, gas diffusion way, and including the catalyst layer. So this has a 500 micrometer value. Okay, then let's calculate its D effective and CR0 to obtain this one. Then most of the terms in this expression are provided by the problem statement. However, it is necessary to calculate CR0. Gas concentration can be calculated from gas partial pressure because the pressure is the concentration is dependent on the pressure and temperature because this is the gas. So how to define the concentration of the gas? The concentration of the gas is expressed in the unit of mole per cubic meter, right? Then let's see the ideal gas equation. PV equals nRT. Then how to get this one? From these relations, N over V, this N and over V is the concentration. And it is expressed P over RT. Then the concentration is P over RT. And in here, also we should consider this P as a reactant pressure, partial pressure, P oxygen gas, and at the channel, and this is the temperature, we already know about it. And this is the CR0 or CO2 0. Then how can we get the pressure, partial pressure? Because we already know that the fractions in this channel, there is a fuel cell, and in the cathode side, the injected gas is, the temperature is 80 degrees Celsius. So if you add the 273, then we get 353 Kelvin, right? And for the pressure, 1 atm, overall pressure is atm. And the oxygen gas, what is the mole fraction of the oxygen gas? The mole fraction of the air is 0.5, 80%, because the water, H2O, the water mole fraction is 0.2. And among this mole fraction, there is air, and there is a nitrogen gas and oxygen gas. So we assume that the composition of this air is 21% oxygen, and the remaining is composed with nitrogen percent. Okay, wait. Okay, then the xN2 air is 0.79, and we should multiply this value to this 0.8, and also xO2 in air is a 0.21, so we should multiply these two values, 0.8 times 0.2. This is the real mole fraction of the air, right? So if you multiply this one, then we get this 0.168 in here. So, and also this is in the unit of ATM, but we should convert these ATM to the postcard, right? So this is a convert factor, and we already know about this general gas constant as 8.314, and the temperature is 353 Kelvin. Then now we get the concentration of the oxygen at the channel in the bulk state with a unit of mole per cubic meter. And later, for later calculation, we have to convert into the unit of mole per cubic centimeter. So in here, be careful when evaluating ideal gas law expression. So by using this equation, the equation from in the textbook, we can derive this one. Okay, let's move on to the next part. To calculate the effective diffusivity, we should know about the porous structure characteristic. For the calculating effective diffusivity, in porous structures, the gas molecules tend to be impeded by the pore walls as they diffuse. The diffusion flux should therefore be corrected, right? Corrected to account for the effects of such blockage. Usually this is accomplished by employing the modified or effective diffusivity. According to Brugman correction, the effective diffusivity in porous structure can be expressed as like this. And in here, epsilon stands for the porosity. Porosity represents the ratio of pore volume to total volume. Usually, fuel cell electrodes have porosity of around 0.4, which means 40% of total electrode volume is occupied by the pores. In open space, the porosity is 1. So the effective diffusivity and real diffusivity are the same. Often, the equation is modified to include tortuosity tau as in this form. The tortuosity describes the additional impedance to diffusion caused by a tortuous or convoluted flow path, highly maze-like or meandering pore structure. Yield high tortuosity values. It is known that tortuosity can vary from 1.5 to 10, depending on the pore structure configuration at high temperature. However, a different correlation for effective diffusivity proves more accurate. So you can choose one equation among these three equations. And let's see, what is the porosity? So if there is a open space, then the porosity is 1. Porosity is denoted by epsilon in here. If there is a blockage or material in here, okay, let's assume this material as B, and the area of this one is A, and then the porosity is defined as A plus A over overall area. So it is smaller than 1 or same with 1. And what is the tortuosity? Tortuosity. Okay, if there is open space, then the particle, the gas can pass through directly through the left, from the left to the right. But if there is a structure in here, they should turn around, okay, like this, pass. So the length of this L2 as L2, and the shortest way is L1. Then L2 over L1 is the tortuosity, which is denoted in here as tau, and it should be higher 1 or the same with 1. This is a tortuosity and porosity. Okay, to solve the problem in the example, we will use this one. But I have some questions about the relation between the tortuosity and the porosity. So I found some paper, and in here they mentioned that there is a tortuosity, there is a very close relation between the tortuosity and porosity. So when you read this paper, the simple tortuosity calculation method proposed here eliminate the need for using complicated weighted averages. The numerical results present here are in good agreement with the empirical relation between tortuosity T and the porosity pi, given by T minus 1 is proportional to the ln pi. So this is the simulation they have conducted. So this is the flow path, and this gray one is the blockage. This one is the blockage, and this is the flow path. Okay, when I read this paper, there is the equation for these two terms of relation. Firstly, we can use this one. This is the tortuosity, and this is the function of the porosity. And in here, P is the parameter. So from the basement of the experiment, the previous study found out this P value. So, and also we can use the other equation in this form. In here, the second equation was found through variational argument in several theoretical studies on diffusive transport. Okay? Diffusive transport in porous system composed of freely overlapping spheres. Okay, freely overlapping spheres. It is the same. In the case of the catalyst layer, they are composed of a very large amount of the sphere particle. So this can be used for the catalyst layer and or various arrangement of cylinder. Okay, the cylinder. Okay, before that. Okay, then we can choose the P value as 0.5 in this, the second equation. And for the cylinder structure, the various arrangement of cylinder, Okay, in the case of GDL, gas diffusion layer, they are consist of large amount of cylindrical fiber, carbon paper, so we can use it for the analysis in the GDL. And in this paper, they suggest the p-value as 1 or 2/3. Okay. So if you need more investigation, just search and apply to your research. Anyway, in here we can use these two types of the equation, but we will use only the first equation to solve the example. Okay, then there is only one variable to obtain the effective diffusivity. We already know about this value, the diffusivity of the oxygen, as 0.2 square centimeter per sec. And in this problem, the porosity is 40%, so we can use the 0.4 as a porosity in here. And then after calculating this value, then we can get the effective diffusivity as like this. Okay, then we already know about the delta in here. This is a thickness of the gas diffusion way, and this is the concentration of the reactant, which is oxygen, and this is the effective diffusivity. And also we should insert 4 in the value of N because the reactant is the oxygen gas, right? So 1 mole of the oxygen gas needs 4 electrons and 4 protons to generate 2 water molecules. So in here we should use the N as 4. Okay, then we can calculate the JL, limiting current density, which is 2.26 ampere per square centimeter. Then note then, okay, we will skip this one. And finally, this is the answer for the A question, and for calculating the overpotential, concentration overpotential, we should use the other equation. And in here, as I said, this is the 0.1 volt in here, and JL, we already obtained this value, so you can insert the value in here. And what is J? J is the operating current density. The operating current density is 2.0 ampere per square centimeter. So finally, we can get the concentration over potential, or the concentration loss, from this calculation. Okay, then let's move on to the transport in flow structures, convective transport. Okay, let's read it together. Wait. The fuel cell flow structures are designed to distribute reactant across a fuel cell. Perhaps the simplest flow structure you could imagine would be a single chamber structure. Okay, single chamber structure. To make a single chamber flow structure, we could encapsulate the entire fuel cell anode in a single compartment, then introduce a hydrogen gas into one corner. But unfortunately, this design would lead to poor fuel cell performance. The hydrogen gas would tend to stagnate, maintain at the corner inside the chamber, and leading to poor reactant distribution and high mass transport losses. Okay, let's draw some schematic of this one. If there is a bipolar plate, this is the chamber, right? This is chamber, and it should contact with the gas diffusion layer. The gas diffusion layer. And if there is an inlet in here and there is outlet, then after we inject the gas H2 or O2 gas in here, it should go through this GDL, gas diffusion layer, and this is the catalyst layer. They should reach to this catalyst layer for generating the electron current. And but in here, the gas don't want to go into this layer because it has a higher resistance than this way. So they just go through the chamber, the single chamber, and they will go out. Our goal is supply the air or the hydrogen into the catalyst layer. But with a single chamber, they will just stagnate, okay, maintain at their position, or easily flow out of the fuel cell. So in real fuel cells, mass transport losses are minimized by employing intricate flow structures. Okay, flow structures containing many small flow channels. Compared to a single chamber design, a design employing many small flow channels keeps the reactant constantly flowing across the fuel cell, encouraging uniform convection, mixing, and homogeneous reactant distribution. So small flow channel design also provide more contact points across the surface of the electrode from which the fuel cell electrical current can be harvested. To make the fuel cell flow structure, the flow channel design is typically stamped, etched, or machined by CNC into flow field plate. The channels, there can be dozens or even hundreds of them, often snake, spider, and twist across the flow field plate, from a gas inlet at one corner to a gas outlet at another corner. Analyzing convective gas, okay, in here. We will learn about the types of the flow channel, but the meaning of here, if we see this bipolar plate, okay, this is the bipolar plate. We call it bipolar plate, and we in here, if we carve some specific configuration of the flow channel, then we call it as a flow field or flow distributor. Flow field or flow distributor. Okay, if you see the bipolar plate through this direction, then there is an inlet, and this is one of the example, and there is a serpentine channel like this one. And also we can design the other way, or we can make it narrow or broaden based on the design rule. So analyzing convective gas transport in these complex real complex real-world flow structures is only really possible. Okay. It's really only possible with a numerical method, which is the computational fluid dynamics, CFD. Okay. But actually, in this chapter, we will discuss the basic analysis of just simple flow scenarios. This kind of basic analysis, which relies on the principle of the fluid mechanics. So that's why we should review some fluid dynamics. Can still yield a great insight into fuel cell mass transport and flow structure design. Therefore, the last of this chapter focuses on applying fluid mechanical principles to simplified convection in fuel cell flow channel. Okay, let's leave the fluid mechanics or dynamics. Firstly, the nature of fluid flow in confined channel is characterized by an important dimensionless number, which is Reynolds number, RE. Reynolds number, is defined as rho VL over mu, or VL over nu. So in here, V is the characteristic velocity. Characteristic is very important because the flow distribution have occur in the channel, like a parabolic shape, right? So, and the L is the characteristic length, and rho is the density, mu is the viscosity, and here nu is the kinematic viscosity. And nu equals to mu over rho. This is the kinematic viscosity, but don't need to remember this one. The physically, the Reynolds number describes, this is very important. Reynolds number describes the ratio of inertial forces to viscous forces in dynamic flow. Regardless of fluid type, flow velocity, or geometry, flows with the same Reynolds number show similar viscous behavior. Okay, in here, the rho VL or rho VD in this study is the inertial force. And this mu is the big viscosity, is viscous force. Okay, then let's take an example for it. In the solid mechanics, if we assume that there is a 3 bores, very bulk bore, then if you through this one to this direction, then this will not affect to the next the 2 and 3 bores. They will not affect the motion of these the other bores. But in the fluid, okay, if you want to move these water molecule or gas molecules, they are connected together. They interact together. So this force is the inertial force. But this molecule wants to go to the right side, but these stagnant molecules will attract this molecule doesn't go to the right direction. So this is the they interact together, and this is the viscous force. Okay, this is the meaning of this Reynolds number. Okay, then let's assume that in the high Reynolds number, the inertial force is dominant than the viscous force, then these molecules doesn't affect to each other. So if this molecule want to go this side and this side and this side, then there is no resistance, very low resistance for this moving. So that's why in the high Reynolds number there is a eddy in the fluid, and in the low Reynolds number, if these molecules want to go offside to this direction, then they go together and they make a layer by layer, right? Layer. So that's why we call it laminar flow. Laminar flow. So this is the laminar flow. In the low Reynolds number means laminar flow. And for the high Reynolds number, it has the turbulent flow. Okay, remember that. Okay, and also the description of the Reynolds number is dependent on the system, which means that internal channel or external channel in the system, we should differentiate the Reynolds number. Usually in here we only consider about the inertial flow, so let's separate it as a inertial flow. Okay, this is the pipe, and we make a flow inside this one. This is the internal flow. So in here, the characteristic length as a d, diameter, not this length, diameter. So we denote this one as a RED. But in this textbook, there is not any word text in here, in the lowercase. And for the external flow, external flow, in here there is a characteristic length is only the length of this one, L. So we denote this one as LEREL, and the definition of RED is then low V, this is the mean velocity, and D over mu, and in here low VL over mu. So this is the difference between these two systems. And also the critical Reynolds number also different depending on this external and internal system, and we only care about this one, internal. All fluids have characteristic viscosity. Viscosity measures the resistance to the fluid flow. On the microscopic scale, the viscosity measures how easily molecules slide past one another when driven by shear force. It can therefore be thought about as a measure of inertial flow, internal fluid friction, and mathematically, viscosity relates shear stress to shear strain. For simple fluids such as water and gases, the relationship between shear stress and strain rate is linear. It's a very important factor. This shear stress is linear, is proportional to mu and shear strain rate. And in here, u is the fluid velocity in the x direction, and v is the velocity in y direction. Okay, let's see this one. This is the Newtonian fluid, which shows this characteristic. And assume that if we assume that a fluid is present between these two plates, where the lower plate is fixed, this is fixed on this position, and the upper plates move to the right at the steady velocity v. Since the plate only moves in the x direction, then we can cancel out this one. Okay, what is the meaning of this one? If this is the fully developed fluid, because okay, if you measure the velocity distribution in this side, it is the same with it has the same morphology distribution. And also, if you measure the fluid flow distribution in here, it is the same. So it is this graph is independent on the x position, so we can cancel out this one if we assume that fully developed. Actually, this is not fully developed. Oh, anyway, this maintain its shapes following through the x direction. Okay, then now we can get only this one, tau xy. And in here, okay, in the state, okay, there is a force measurement of attract this plate, upper plate, as tau. Then in the steady state, there should be a resistance in this direction, tau, and this is the shear stress. And if you have very sticky fluid in here, then there will need more shear stress to maintain this velocity. Okay. So if we the tau and the viscosity is proportional, and also it depends on this profile. So we can define the tau xy as mu times the velocity gradient in here. And this is the linear shape of this velocity profile. So we call it as a Newtonian fluid. And in here, there is a very important critical assumption to obtain this one, because if the plate moves with a velocity v, and this side, okay, in the contact point, the water, the fluid also should move through with the v. This is called as a no slip condition. Okay, no slip condition. This is the critical assumption for getting this one. Anyway, we can know the relation between the shear stress tau and the mu. So it is very important to obtain the mu value for calculation of the fluid behavior inside the chamber or GDL or the catalyst layer. Okay, now we can define the mu, the meaning of the mu, viscosity. Considering the microscopic origin of viscosity, it is not surprising that mu is strongly temperature dependent. Viscosity increases with increasing temperature for gas. It is proportional to the viscosity is proportional to temperature. And for dilute gases, the temperature dependence of viscosity can be approximated either by simple power law. Okay, this is the first equation we can use, or by Sutherland's law using the kinetic theory of gases. Also, we can use this second equation. Anyway, the viscosity is the proportional to the temperature, and depending on the kinds of the gases, this is varied. This varies. And also there is S in here. This is the variable in here. Okay, you can find this N value and S value by referring to this table. There is S and N in here, and the N, S are depending on the types of the gas. Okay, in here, the air, oxygen, nitrogen, hydrogen, and water vapor has these values at STP. Okay, remember that. We will use this value for solving problems. Okay, viscosity is also pressure dependent, right? But increasing slowly with increasing pressure, right? Pressure also it is proportional to the pressure, but fuel cell rarely operate at gas pressure higher than 5 atm. At this low pressure, this is comparatively low pressure, the low density limit for viscosity applies. So the pressure effects on viscosity can be safely ignored. Thus, viscosity pressure effect will not be considered in this textbook. The viscosity is proportional T and P, but we will ignore this pressure effect. Fuel gas streams are rarely composed of single species. Instead, we usually deal with a gas mixture. It is very important. We use the gas mixture. Gas mixture, oxygen and nitrogen gas. The following semi-empirical expression provides a good approximation for the viscosity of the gas mixtures. So from here, we assume that in the air, the oxygen gas, the fraction of the oxygen gas is 21%, and for the nitrogen gas as 79% in the air. And by using this assumption, we can calculate the viscosity of this air gas mixture. And if you see this equation, if there is a three gas molecules, then we can use this N as 3. And also in the denominator there is a terms like this. It seems like very complex, but actually it means the interaction between the mixtures. Okay, if you see this pi in here, pi ij, then this is the there are two species, Mi and the I and J, and the ratio between them, the molecular weight and the viscosity of each species are included in these pi terms. So we can calculate this interaction term, and if you insert in here and overall if you make a summation over all these terms, then we can get the mu mix, the viscosity of the gas mixture. And in here, Xi, Ji are the mole fractions of species I and J, and M in here is the molecular weight, gram per mole or kilogram per mole. And the fuel cell flow channel, in the flow channel, the boundary between laminar and turbulent flow is determined by the Reynolds number, as we discussed. Laminar, turbulent. So to make this critical point, we use the Reynolds number as 2000. And while the turbulent flow occurs for over the 3000, but if you set only one value, then for the internal flow with the diameter of this circular shape is RED is about, okay, critical value critical is about 2000. Okay, also if there is an external flow, this is the internal flow. If there is a flow like this and with the characteristic length as L of the plate length, then RELC is about 5 multiplied with 10 to the 5. Okay, and as I said, we only consider about this case. Okay, then let's move on to the other example. Consider a fuel cell operating at 80 degrees Celsius. In the cathode, humidified air 1 atm at 1 atm is supplied with a water vapor mole fraction 0.2. If the fuel cell employs circular channel, this is very important factor, circular channel with a diameter of 1 millimeter, find the maximum find the maximum tolerable air velocity that still ensures laminar flow. Okay, we should find the velocity to make the turbulent flow. Okay, so if the velocity of the flow is increased, then the Reynolds number will be increased, and the laminar flow can convert to turbulent flow. So the meaning of the question is that find this point to make find the velocity to make this transition. Okay. Okay, then let's see this equation first. Okay, the Reynolds number is rho Vd over mu, and in here this is the gas mixture because this is the air. So mu mix, we should need to find the mu mix in here, and diameter is fixed, and rho, we don't know about the rho, right? Rho, and we should get this V. So there are two terms we should find. Firstly, in this example, they solved this mu mix. They found out the mu mix first. Okay, when referring to this equation, mu mix, we need to know about each the viscosity of each species. So firstly, let's talk about this one. To find out the viscosity of each species, then we should use this one because it is dependent on the temperature, operating temperature, and the operating temperature is 80 degrees Celsius, not a room temperature. So we will use the first equation to obtain its viscosity. And firstly, we will get the viscosity of the nitrogen gas at 80 degrees Celsius. So if you insert the temperature in the Kelvin unit, and we should find out the mu 0 at the STP, and also we should find out this one, mu 0 and n, for the nitrogen. So where is the nitrogen? Nitrogen has the mu 0 as a 16.63 and n is a 0.67, and s we don't consider about the s in here because we use only the first equation. So if you calculate this one, we can obtain this viscosity. And similarly, we can obtain the mu oxygen gas and water vapor in the same way. Okay. Now, then we should get the mu mix, right? Then we can refer to this equation. Okay. It is very somehow complex, right? So let's solve it together. Firstly, okay, we can make a number of N2 as 1 and oxygen as 2, water as 3. And to calculate this one, we should know about the mole fraction of each species and viscosity of each species too. And firstly, to get the Xi mole fraction, we already know about that. Water molecules, the composition is 20%, okay? And the N2, oxygen and nitrogen gas, has the volume of this fraction. And if we multiply the 0.8 to this one, then we can get the real mole fraction of the nitrogen and oxygen gas. And also we already know about the molecular weight, Xi and Mi, because the atomic number of the nitrogen, then there is a proton and neutron, and the gas has 2 atoms. If we multiply this one, then approximately we can get the molecular weight. Okay, you can find it in the table, the other table, but actually we can get this molecular weight directly from the calculation. And also we already know about the mu I, the viscosity of each species. Okay, then to get the mu mix, we should insert the I1, I2, I3. Okay, to obtain the mu mix, X1 mu 1. If you insert the I to as 1, then there is A1. Okay, this is A1 because this is somehow complicated. So we denote this one as A, and X2 mu 2, A2, plus X3 mu 3 over A3. Okay, then this is very complicated to get this A1, A2, A3 for each. So, but actually this one is very simple, right? X1 x1 is here 0.632, and the mu1 is 1976. And next time, as a next step, we should get is a1. So after you insert 1 in here, this is ij, pi ij. So firstly, we insert 1 into the I, then the I1, j starting from the 1 to the 3 here, okay, from the 1 x1 pi 1 1 plus x2 pi 1 2 and x3 pi 1 3, okay, to calculate only this a1, right? And the pi 1 1, pi 1 2, pi 1 3, we should get this one. In here there is a relation. So to obtain this one, we make a table like this one, because there is a ratio between the molecular weight and the viscosity ratio. So to get this one, we should know about m1. Okay, this is simple. So for this one, we should know about the m1, m2, and mu1 over mu2. To calculate this pi, then we should know about this ratio. Okay, then we already know about the molecular weight of each species. Okay, in here, the pi 1 2, to get the pi 1 2, okay, 1 2. So this one m1 over m2, and this one is mu1 over mu2. And then if you insert these two values, mu m ratio, viscosity ratio, in here, then we can get the pi value, pi 1 2. And then finally, there is the mole fraction of the x2. So if you insert the x2 in here and multiply it together, then we can now get this 0.156. Okay, for the other one, 1 1. If we want to get this one, then this is the molecular weight ratio, viscosity ratio, pi, and x pi. And for the other third term, this one, then you can calculate this value, and this is the final term. So if you sum up of all this one, then finally we can get this a1. This is a1. And in the same way, we can calculate a2 and a3. So if you insert each value into here, then this is the first term, second term, third term. Then finally we can get the mu mix. It's like this. It is somehow complicated, but step-by-step solving is very make it easy for solving. So the molecular weight of the mixture is given by m. Why do we need this term? Okay, let's talk about it. As I said, we should get two terms to obtain the Reynolds number and velocity relation. Firstly, we get this one, and nextly, we should get this law of this gas mixture. Then how can we get this one? What is the law? Law is the density. density is m over v. Okay, remember this is law, and from the either gas equation, PV and RT. And in here, this is more number, right? More. And how can you convert it to the mass? If there is a molecular weight and if there is a n more, then that is the mass of the gas. Okay, then we can convert it to small m over capital M. Then PV equals is expressed in this form. And there is V and M in here. So M over V equals to PM RT. Okay, this is the density, gas density. To obtain this one, we should know about this value: molecular weight and pressure and the temperature. And this is the general gas constant, which has the value of 8.314, and we should express the temperature in Kelvin unit, and this pressure is actually 1 atm, but we should convert it to the Pascal unit. And finally, we should get this one, molecular weight of the mixture. So we'll solve for the M mix. M mix, okay. Then there is a mole fraction of each species, right? So we already know about this each mole fractions, xi and mi. Then we can get this molecular weight of this mixture. And then if you insert each PMRT in here, in the Pascal and the Kelvin, this is Kelvin, then we can get this, the density of this gas mixture. Okay, now we obtain all the variables for calculating the V, right? So the Lehner's D equals mu low VD, and we should know about this V, and we insert 2000 in the Lehner's number. So V is expressed RED max and mu over low D. Okay, in here L, it is not correct. We should use D. The diameter is 1 millimeter, so we should use a meter unit. And if you calculate this one, V max is 38.03 meter per second. Actually, if you find the other related materials, then the air fan, in the very strong wind mode, is about 5 meter per sec. So it is almost impossible to generate this velocity. It is higher than the typhoon. Okay. It is a very high speed, so I think it is really hard to get the turbulent flow in the channel, in the circular channel. So we will consider about the laminar flow in the fuel cell structures. So okay, from now on, let's move on to the next chapter. Next chapter, mass transporting flow channel. Okay, actually, when analyzing the flow in turbulent flow, it is almost impossible. But in laminar flow, we can start from the Govern equation, and we can derive some specific relationship between each terms, like Reynolds or the friction factor or friction coefficient, something like that. So that makes it somehow simple to analyze. The pressure drop in flow channel. This figure illustrates the typical mass transport situation in a fuel cell flow channel. In this diagram, we have a gas moving from left to the right. Okay. Through the flow channel at mean velocity u. Okay, this u is very important because, as I said, the velocity distribution looks like a parabolic shape, but actually we should define the representative velocity. This is the mean velocity. Okay, this is the mean velocity, and this flow is induced by the pressure difference. If there is a P in and there is P out, the delta P always should be calculated in P in minus P out, because it has always higher than this one. Pressure difference between the inlet and the outlet drives the fluid flow. Increasing the pressure drop between the inlet and the outlet will increase the mean gas velocity, improving convection. Okay, delta P, if increase, the velocity it will be increased and the convection will be increased. For circular flow channel, the relationship between the pressure drop and mean gas velocity may be calculated from the relation. Actually, this relation can be derived from the Govern equation from the fluid mechanics, but actually we will skip in this part. So the meaning of this one is the delta P, okay, pressure drop, is proportional to the tau, which is the shear force of the fluid, shear force. And also we already know about the friction factor. In here, okay, the mean shear stress is expressed tau bar, and non-dimensional number, the friction factor F. So we have the other relation between the F and the tau. And also we already know about the Reynolds number, like this form. And okay, let's assume that is very important. F times Reynolds number has this constant value for laminar flow, only for laminar flow, and mostly important in the circular channel. Okay, this is only applied to the circular channel, but in the rectangular channel we can apply this relationship between because this one also is derived from the circular channel Govern equation. So anyway, from these three equations, 1, 2, 3 equation, we can make a relationship between the pressure drop and the velocity and the geometry. Okay, let's calculate it. There is not enough space. Okay, let's write down in here. Firstly, dp dx. dp dx equals to 4 over d tower hat. The first equation. And the second equation is the tower is expressed in the with the friction factor. So okay, F low u bar square. This is the second term, and finally we already know about the Reynolds number. So we multiply the Reynolds number in the over and down. Okay, let's move this one to okay, here, and the Reynolds number, and in here F. And we already know about that in the circular channel, this has the constant value as 16. So the value of this one, 64 over d and if we write down the Reynolds number in here, low u bar d mu. Okay, then we can cancel out these okay, 32 and low, right, and u in here, and finally we get that t square 32 u par mu. Okay, so if we want to know about the pressure drop through the channel, so if we the meaning of this one, if the flow fluid flow by 1 meter, then this amount of the pressure drop happens, and it can be simply calculated only in the circular channel. Circular is very important, and laminar. If we know about the geometry of diameter and the mixture, the viscosity of the mixture and the mean velocity of the flow, then we can get the pressure drop. We can calculate it, and in here, okay, there is a missing one. Okay, we should multiply mu in this side, right? Okay, so this is very important to calculate the pressure drop through the channel. And the next, unfortunately, the most fuel cell flow channel are rectangular, right? Rectangular instead of the circular. For rectangular channels, equation cannot be used. So for rectangular channels, we must use hydraulic diameter, dH, in here to compute the effective Reynolds number compared to circular channel. And in here, dH can be obtained from this equation. In here, A is the A is the cross-sectional area. And this is P is the perimeter. Perimeter means this one. Okay. Okay, in here, let's assume that there is a circular channel in here. There is a representative characteristic length d, and if we calculate the dH in here, 4A over P. What is A, cross-sectional area? Pi d square over 4, and the perimeter perimeter is pi d. So this is cancelled out, and finally we get d. And how about the rectangular shape? Rectangular shape. Okay, we assume that in the textbook 2a and this is 2b. The meaning of this a is the channel width, and this b is 2b is channel height. So what is the TH for this channel? TH for cross-sectional area for AB, and perimeter is 2, okay, for A plus B, and then we get 4AB over A plus B. This is the hydraulic diameter of the rectangular shape. And how about the square? In the square, A equals 2 B, so 4A square per B square, 2A. So 2A is the hydraulic diameter. The length of the one, this one. Okay, this is the definition of the hydraulic diameter. So if you find this one, then you can solve this. You can insert this d into the Lagrange number. Okay, and also mostly important, the four rectangular channels, the relationship between Lagrange number and friction factor is also different from the circular. Okay, different from the circular channel, because the circular channel has a constant value of the F Lagrange, but it depends on the aspect ratio of the rectangular channel. So from the experiments, researchers have found that F Lagrange number is like this, and the alpha star in here is the only variable in this equation. So alpha star is the aspect ratio of the channel. So in here, aspect ratio means B over A. Okay. Then by determining tau W for rectangular channel from the upper equation, the pressure gradient can then be determined by using this equation. Okay, let's solve the example 5.3. Fluid is flowing at a velocity of 1 meter per sec through a 1 millimeter wide, 2 meter high, 20 centimeter long rectangular channel. Find the pressure drop in the channel if the viscosity of the flowing channel, flowing fluid is this value. Okay. To solve the pressure drop, right? Pressure drop dp dx, and if we multiply the length, channel length, then we can obtain the pressure drop through the channel. In here, this is mu and velocity. Okay, this is mu u, and wide, I just said, this is width a, this is 2a, and this is height, right? Height 2b. And this is the length L. Okay, from the start, from these relation, because we already know about the F times Lagrange number for the circular channel has the constant value, but it is not the circular channel anymore, so it is just a rectangular shape. So we should use this relation to solve this problem. So from the start, this one, we already derived this one. F Reynolds number should be achieved. To calculate this one, we should know about the alpha star, right? Alpha star in here, aspect ratio, and 1 millimeter wide. Okay, 1 millimeter wide and 2 millimeter height. Okay, the aspect ratio of this one is alpha equals B over A. The value of this one, wait. Okay, let's repass this one. Okay, just convert, exchange this two value with height. Okay, and then this is now A to A, and this is to B. So B over A is half, right? 0.5. And then the alpha, we now know about the alpha in here, and from the equation in here we can insert the alpha to obtain the F Reynolds. F Reynolds now is obtained as 15.56. So using, and also, okay, for making this one, and also we should know about that the one number dh. Okay, one variable dh is 4a over p. So this one, the cross sectional is 1 times 2, and p is the summation of this value, the perimeter. So we can get the 1.33 millimeter, and you can change it to the meter unit. And finally, we already know about the mu and u in here. If you insert this value into here, then dp dx is calculated. So the final result is 315 Pascal per meter. So to obtain the pressure difference between the inlet and the outlet, and then we can multiply the channel length to obtain only the Pascal unit. P drop is now, okay, we already assume that this is a linear. Then if we multiply this L length, then this is, we obtain the 63 Pascal for this channel, for the pressure drop designed in this channel. Okay.